Right?
Now I do. We
Excellent.
were having private discussions, so I suddenly realized we were broadcasting it.
I continue with Steve.
Talk about?
Me too. Yeah, so, right. So I talked about things that I hope I put out interesting ideas, but I also know I communicated the fact that about the underdoped cuprates, I think there are many things that are really puzzling, which of course means they're interesting and you should be interested in them. I focused on properties that directly have to do with the superconducting state and only with thermodynamic quantities. In particular, there was this observation that T theta is small compared to T delta, and that this was an interesting thing and needs an interesting explanation. I didn't mention lots of other really interesting and, which is to say, confusing aspects of the behavior of the underdoped cuprates. Many of the things that are of most interest to me, concept of intertwined orders, which is a descriptive term. It's not a theoretical term, but it says that it's the observation that for some reason there seem to be lots and lots of different types of ordered states that are all there. You can't get rid of them. They appear together. They all have very comparable condensation energies or ordering temperatures. They interact with each other in complicated ways that are sometimes cooperative and sometimes antagonistic. And I think it would be nice to understand where this comes from. There's most, if you look at the phase diagram of lead, there's a normal metal state, and there's a superconducting state. And if you alloy it with tin, you still have these two phases. And okay, sometimes you can have some other phase and you can have a multi-critical point, but to get to a multi-critical point, you have to tune two parameters. And here there's this broad range of materials, temperatures, and dopings where all of these things are there on comparable strengths. That's not normal. It does seem now to be normal materials we study because they're high temperature superconductors. So maybe the degree of fine tuning that you say, I'm looking at materials that exhibit high temperature superconductivity, maybe it brings these things along with them. But okay, how that is not understood. You stopped me at a good place. There's all the pseudo stuff in this. There's pseudo transport phenomena, although maybe in thermodynamics was before. And so I'm moving away from that today, and I'm going to the overdoped side of the phase diagram. Where Tc does this, T delta does this, and T theta does this. And where I found that I think that I know what this would look like if you didn't have disorder. And I claimed that Tc would look like this, that T theta would look like this, and T delta would look like this. and that Fermi liquid plus BCS theory is applicable. Okay, so this phase diagram doesn't look like the experimental phase diagram. So I'm going to have to convince you that I can understand the theory I'm describing to you is useful and in conflict with experiment. But pause for a minute and understand what's in it for us. What's in it for us is if this is true, then I can really understand, I can hope to understand conductivity, at least why TC grows and gets big if you approach it from this side. It doesn't explain why it doesn't keep growing, what causes it to cap out and fall down, but we would have understood a very important piece of the high temperature superconducting puzzle. There are a couple of other things that I will mention here that are inconsistent. I think I mentioned that was inconsistent with my picture, which is that if I then here we see something that's not what's expected of weak coupling either. We see one version of a strange metal, whereas in my picture over here, all of this would be a ferrous liquid metal. Now, we did just have talks from Dmitry Maslov on materials that are good Fermi liquids, where we don't understand all sorts of anomalies about the transport. And this strange metal, the anomalies here are on transport. So, maybe it's not as threatening as it would have been if we didn't understand that our ignorance is broad. But at any rate, I'm going to try to explain, or at least make first steps in explaining why in the clean system this will disappear. And then I'm going to also discuss some, falsifiable predictions that could be made on the basis of this. And I'm going to preserve that. The other about this is if this perspective is right, then I know tools I should be using, what theoretical tools I should be using the tools of liquid theory and BCS theory. So, it doesn't mean that the system's, intrinsically weakly correlated over here. I mean, the microscopic physics is the same, strongly correlated, coppers and oxygens and all that stuff is ever, but it means that somehow or other at some intermediate scale, maybe notionally J or something, over here, the system settles down into some renormalized problem, which could be described by weakly interacting quasi-particles, possibly with renormalized character, and with some interactions that come from integrating out the high energy degrees of freedom. Since I'm not taking a quantum critical perspective, so if I were taking a critical perspective, I would need to also have some quantum critical modes as part of my low energy physics. I'm imagining that over here you integrate out the high energy degrees of freedom, and the only low energy modes are the energy modes of Fermi liquid. Means that although I don't know exactly what the residual interactions are between the Fermi liquid quasi-particles, they should be local in space and time because they've come from integrating out high energy degrees of freedom. So that's what I know, and I mean that's what I know if my conjecture is right, and now I want to try to see what we can understand from that perspective. So, good. And now, I really would have liked to have done all of this on the board, but first place, my fellow lecturers were way too interesting. I wasn't able to work on my notes during lectures, and you all were so good at pretending you were interested in hearing what I was saying over meals that I spent all my time talking to people. So I'm going to use transparencies, but pretend it's on a board and interrupt me as much as if I were writing on a board. Anyway, I apologize for that. This, by the way, is the view over the Pacific from Pacific Palisades, which is my hometown that burned down. So, good. So even from this BCS perspective, the cuprates have some things that are different from conventional superconductors. So the first is that they're D-wave, and what that means is that their sensitivity to disorder is quite different than that of S-wave superconductors. And that's going to play a role. I'm going to try to explain everything in terms of disorder, but disorder is a much more serious thing for a D-wave superconductor than it would be for an S-wave superconductor. And, whoops. Secondly, the correlation length, the coherence length of these superconductors is reasonably short. It's on the order of a few lattice constants. As we discussed, it's a little bit vague exactly what I mean by the coherence length, but any estimate people make of the coherence length, it's a few lattice constants. And that's very different from conventional superconductors where typical correlation lengths are maybe 1,000 angstroms or several hundred angstroms. And that's going to lead to another feature of the disorder physics, which is different from that in conventional superconductors, which is it's going to lead to a breakdown of effective medium descriptions. It means we're going to be thinking in terms of rare events rather than average behaviors. And so these were, the title refers to a title of a talk I gave at a conference in Germany last week, but which I called Super-puddles because I needed a title. But anyway, the point is this is going to lead to, even in materials that by solid state standards we would generally say were homogeneous, but that the electronic structure will organize itself, self-organize itself into a inhomogeneous electronic structure. It'll look like puddles. Okay, so that's where I'm going. So first, let me look at the problem of disordered superconductors. And let me remind you of Anderson's theorem first. So what Anderson noticed is, so let's see. We're going to characterize the disorder by a mean free path. And we're going to characterize the superconducting state by the superconducting coherence length. And in conventional superconductors, the coherence length is long. And that means that as we turn up disorder, there are two regions. The region where L is much bigger than xi naught. So that's the very clean limit. And obviously, any idiot would know that that's going to have no effect on the superconductivity. I can do calculations of TC or superconducting order, ignoring the disorder. But then there's a region where xi naught is much bigger than L, but it's still much bigger than a lattice constant, or more precisely, bigger than 1. So it's still weak disorder from the metal. So we can still be using conventional metallic physics. And here you might have originally thought that this would destroy superconductivity. And what Anderson showed, and it's a simple physical argument that you're pairing time-reversed pairs of states rather than states with different momentum. but you can also understand it diagrammatically by including the appropriate vertex that this has no effect on superconductivity. So in both these regions, we're going to get the same value of delta naught. We're going to get the same TC. It's going to be insensitive to the disorder. And this is very important because, in most metals, only in most practical superconductors, you're not remotely satisfying this condition. So if this limit wasn't possible, you wouldn't have practical superconductors. Yeah.
Can you say more precisely, like insensitive, what's the correction? As opposed to, if it was that D wave.
So I'll get to D wave in a minute, but for S wave, in this, there's really no correction, or there are corrections of order, KF squared probably, maybe 1 over KFL. No, but parametrically small in 1 over KFL. Okay, and this is really a wacky proposition. I mean, I give you a piece of metal and I tell you to calculate, TC. And so you measure the electron phonon coupling, maybe by looking at the T linear at high temperatures, and you measure the density of state, the phonon frequency, whatever it is you need, and then you say, I'm going to ignore disorder, and I calculate TC, and I calculate the evolution of the superconducting order, and I get the right answer. On the other hand, if I calculated the resistivity, say, at TC, so the resistivity at TC would be, something like T squared over EF, as we've just heard. I mean, if it were clean. And instead, the resistivity is KFL. And so, we're many orders of magnitude different in the conductivity. So if I asked you to do the conductivity ignoring the disorder at this temperature, you would just be wildly over electrons. But if you ask me to calculate things about the superconductivity, get them dead right. Really? Okay, and so this is called the clean limit, and this is called the dirty limit. And I know all practical superconductors are in the dirty limit, so this is very important. Other than S-wave superconductors, within BCS theory, things behave much more like you would have guessed without doing a calculation. So, and there's the Abrikosov-Gorkov theory, which treats the disorder in an effective medium approximation and then calculates TC. What you find is that TC goes to 0 when L gets to be of order C. And there's a specific calculation. There are explicit functional forms that you can write down. This is for D wave or any other unconventional superconductor. We'll find that TC is equal to TC naught times some function of C naught over L, where C naught is the clean limit coherence length. So of 0 goes to 0 as x goes to infinity, and there's a critical value, I think it's L equals something like 0.16, something like that. No, other way around. Well, anyway, there's some number where L is of order C naught, and you destroy superconductivity. Yeah. What? So if you do the same theory if you do the same theory, the Abrikosov-Gorkov theory for superconductivity, you recover Anderson's theorem. So there's a physical notion that what's happening is that, think about an electron propagating, and the time scale you're interested in is going to be 1 over delta. Delta is the gap. That's the time scale over which you know that you're in the superconducting state, not in the metallic state. And so you're scattering many times on the Fermi. If you're in the dirty limit, you're scattering many times around the Fermi surface on this time scale 1 over delta. And so if you're an S-wave superconductor, that's okay, because each time you sample the gap, you see the same value. So you average the gap over the Fermi surface, but the average of the gap over the surface is equal to the gap, so it doesn't make any difference. But if you're in an unconventional superconductor, if you average the gap over the Fermi surface, you get 0. Okay, so that's the sort of physical intuition about why things are so different. Yeah. Doesn't help. No, it's the gap. It's not the magnitude of the gap that you're measuring. So this would be true for any for BCS theory of any unconventional superconductor. I mean, if you had a D-wave superconductor in an orthorhombic system, so the average of the gap isn't exactly 0, then you would go from TC in the clean limit to a new TC, which corresponds to what the average gap is around the Fermi surface, and now you would be in a superconductor. Yeah.
So in the S-wave case, even when you're in the dirty limit, there's just some new gap, but it's not a new TC, but it doesn't go to 0.
In the S-wave superconductor. Yes. No, I mean, look, to 0th order, to the extent that the gap, that you're in a simple S where the gap is K independent, there's really no effect on TC. So if
dirty limit, it's not like there's a
right.
It's not just the value. Okay, the value changes. But
the value doesn't change. Not even the value changes. It doesn't.
There's
no
function C over L.
Yeah.
That's fine.
So in this case, if you had, so in the simple S-wave limit where the gap is isotropic, TC is equal to TC naught times F of C naught over L, and F of X is equal to 1. It's true. If you have some more structure to the S-wave, so the gap is non-zero, has non-zero modulations, then you have some small correction to this. Now, all of this changes when when you get dirty enough that you start having localization effects. If the localization length gets to be comparable to its length, then you have some effects. If you weren't in this weak coupling limit, so here I have C naughts much bigger than a lattice constant, so this is all weak coupling, then you might see some things due to the structure of the density of states. But this is a correct asymptotic statement. Yeah. No, that's the point. The mean free path has no effect on TC whatsoever.
Causes fusion gets slower.
So first place, that's not BCS theory, and second place, that's probably not true. But third place, that's an effect on mu star, more or less. So this is just within BCS theory. Oh, like just electron phonon interaction. Okay, I mean, it's really, it's astonishing. You get the right answer. Really the right answer, not even just roughly the right answer to this important question by completely ignoring disorder. It still boggles my mind, so yeah.
When L and the mean free path and the correlation length are comparable, TC goes to 0?
For the unconventional superconductor, yeah. No, so there's a critical value here. So there's F of X is equal to some ratio of these. I have it in my notes. I can look it up, but it doesn't really matter. Yeah.
Quick limit bigger than A.
So in doing all of this, I've done metallic physics. So I've assumed I have well-defined quasi-particles that are propagating, and I've assumed, things that have to do with the energy dependence of the density of states. I replace the density of states by the density of states at the Fermi surface. I do all the conventional things that we do sort of reflexively, but really are reflecting the fact that the superconducting TC is parametrically small compared to E Fermi. So I'm taking advantage of the parametric smallness of TC over E Fermi. Yeah. Mm-hmm.
When we add more and more disorder, that the phase fluctuation of the superconductor also.
Oh, so in this limit, so yeah. So the question is, disorder suppresses the superfluid density. So can disorder get us into a regime where we have phase fluctuation dominating? And the answer is no. What happens is the superfluid density is, kappa, what I was calling it, is equal to kappa naught times a function, again, this same parameter, but let me just for the dirty limit. So it's delta naught divided by h bar over tau. So but this is, yeah, so what am I trying to say? Yeah, so if we were doing this in 2 dimensions, since delta naught is TC, this is proportional to TC. And so that sounds good. It sounds like I'm going to get T theta to be comparable to TC, but at least, so in 2D, at least, there's a proportionality constant here, which is KFL, which here is still big. So although the superfluid density drops in proportion to TC, I mean, the disorder itself doesn't suppress the superconductivity. I had fixed disorder and I say turn down lambda as a way of dropping down TC and getting into the dirty limit, I would still see the superfluid density dropping in proportional to TC, but I still wouldn't be in the phase fluctuation regime because the superfluid density would still be large compared to TC. That's what I was trying to say. Other questions? Yeah. So really what I meant here is any gap that averages to 0 over the Fermi surface. And so now there are things like S plus minus where the gap doesn't average to 0, but it averages to something much smaller than the typical value. So, that's somewhere in between, but for many purposes, that should be like an unconventional superconductor. What? For this, so unconventional includes P plus IP, D plus ID, Q, whatever. So, really the essential feature is the average gap more or less equal to the root mean squared gap, or is the average gap much smaller than the root mean squared gap? Okay? Any other questions? Okay, so now Right now, so there's a piece of physics that all of this argument misses, and that's it. We've talked about, for instance, the mean free path. But, you know, if I have a disordered system, if I look at different patches of the system, you know, this is a disordered system. So there'll be different numbers of impurities or different configurations of disorder in each of these patches. And so there's going to be a different mean free path in each of these. Now, for an S-wave superconductor, that might not alarm you very much, because I would calculate TC here, and I calculate TC here, and I calculate TC here, and I calculate TC here. And even though these mean free paths are different, they're all the same. Well, let's see. Assuming this, I've assumed that these patches are big enough that it makes sense to calculate TC. So let's make these patches large, say larger than psi naught. So, okay, that's great. The system was inhomogeneous, but my superconducting state is homogeneous. I don't really care. But if this is a D-wave superconductor, then if these fluctuations are significant, then maybe in this patch, TC is 0, and in this patch, which happens to be a bit cleaner, TC is big. And now I suddenly have quite a different problem. Yeah.
Usually we assume that there's macroscopic homogeneity.
Yeah, I'm assuming that.
So these fluctuations in part, that becomes smaller.
So here, if L is the size of the patch, let's say I have impurities. So the concentration, the number of impurities inside each of these patches, or the concentration, N over L squared, is going to go like, you know, like 1 over L. So in usual, even D-wave superconductors, pick L to be big compared to the clean limit. So suppose I'm looking at strontium ruthenate. So coherence length is 1,000 angstroms. So these patches are at least, you know, 10 to the 5th, 10 to the 6th, I don't know, unit cells. The fluctuations in the mean free path from one cell to the other are clearly going to be negligible. But in the cuprates, where the coherence, the lattice constants, these are going to be significant. So there are two things that are going to make these consider. I mean, these considerations are general, even in the context of S-wave superconductors, but they're sort of theoretical curiosity. They're rare events that are so rare that you should ignore them. But for a D-wave superconductor with a short coherence length, these are order 1 effects. So that's what the main message of this talk is going to be, is that if I take just BCS theory, if I do BCS theory, I'm going to do BCS mean field theory. In fact, from now on, for quite some time, I'm going to do nothing but BCS mean field theory. The only thing that I'm going to do is I'm not going to treat the disorder in an effective medium approximation. So I'm going to write down a Hamiltonian, which is some electrons moving on a lattice with some type of disorder in it. And I'm going to have some interaction, which, if you want, could also be disordered. We looked at that. You know, maybe some places the attractive interaction is strong, some places it's weak. And I'm going to treat this in mean theory, writing down a trial Hamiltonian naught plus, sum over R and R prime of R and R prime times CR up, CR down, plus Hermitian conjugate. And I'm going to compute delta variationally, which is going to give me a self-consistency equation that says that delta of R and R prime equal to some interaction times C dagger with various indices, which I'll show in a minute. And I just solve that either notionally or numerically. So it's all mean field theory, but I haven't done any averaging over disorder. I'm treating the disorder seriously and the correlation effects in mean field theory. Yeah.
So, I mean, this thing would suggest that you could have different domains where you would have either superconductivity or no superconductivity.
Yes.
So one could try to put this in a magnetic field, see if flux line pass through certain regions,
Yes.
and then check for the density of disorder in these regions.
Okay, so it's a good point, but now, here there was a very important, I broke this system up into regions of size L, and what I get it both depends on if I'm looking at an S wave or a D wave superconductor, how sensitive I am to variations from one region to another, but it also depends very sensitively on L. So if I'm looking at the magnetic response of the system, length scale involved is the penetration depth. So at least in strongly type 2 superconductors like the cuprates, the penetration depth is very much larger. So the problem can be extremely inhomogeneous when we look at pairing or at single particle spectra, and absolutely homogeneous in the magnetic response system. Okay, so, this is a little bit different way of thinking about systems. This is a familiar way of thinking for people who are deeply into disordered systems, but people who are into solid state physics. A new, different way of thinking. You have these different length scales at which the behavior is different. At the beginning of the Sentil's first talk, he talked about our sort of religious commitment to quantum field theory or field theoretic descriptions of emergent phenomena. These sets of rare events are things that act uncomfortably with the field theory description. It's not that you can't include them, but it requires special care. Okay, any other questions? Okay, so good. So let's see, what do I have here? So I think I've said all of this already, fortunately. Okay, so here's what we're going to do. We're going to do BCS mean field theory. So I've described this. That's my trial Hamiltonian. I'm going to solve the mean field equations. And here, A and B are, you can think of them as being, say, position lattice. But, if you wanted to be thinking about multi-orbital superconductors, they can have orbital indices, they can have spin indices. I am going to make, in a minute, an assumption, which is I'm going to assume that whatever they are, both the terms in H naught and the terms in V are short range in space. And now this equation, which is the full gap equation, can be linearized to find TC. The way you do that is you replace this. Is there something I can point with? Ah, good, that's better. Now I'm armed. So I replace this expectation value by its expansion in powers of delta. And so I have here, this is some normal state superconducting pair field susceptibility times the applied gap construction and higher order. And so this gives us a linearized gap equation that can be written in terms of this matrix, which I've just done to make this matrix Hermitian. And if my Hamiltonian's time reversal invariant, it's also real. And it's also, so these are the superconducting susceptibilities. These are properties of the normal state, including all the effects of disorder and of temperature. V is the effective interaction, which is again short range in space, presumably temperature independent because it came from integrating out high energy modes. And then O is that identify TC by looking for eigenvalues of this gap equation. And when I get the first eigenvalue whose value is bigger than 1, that's TC. Right, this is familiar to everybody? Now, I'm going to not only be interested in the largest eigenvalue of this. You know, sometimes these states are going to be localized. And so I might find a solution here when some state here has an eigenvalue that's bigger than 1. Then I might find some other state over there that at a slightly lower temperature has an eigenvalue that gets to be bigger than 1. In the usual case where one eigenvalue gets to be bigger than 1, I get superconductivity everywhere, then that sort of quenches any other solutions. But here I might be interested in multiple solutions. So I'm going to be interested in calculating this eigenvalue spectrum. So I'm going to order them somehow. And now the important thing is that this matrix has a spatial range that's either in the clean limit V Fermi over T, or in the dirty limit, it's the Thouless length. Okay, so yeah, and just, you know, if I then, you know, normally what I would do is when I found one of these where lambda was bigger than 1, I would then include higher order terms, and I would find that the gap grows like the square root of lambda minus 1. And but I'm going to focus for now on just the spectrum of these eigenvalues. And so rho is the density of states for these eigenvalues. So everybody's happy with this. You know what I'm talking about. Okay, and so here we've done some calculations. I'll comment on what they mean, but let me just, this is my numerical experiment. So what have we done here? So I've taken an interaction which is repulsive on site and attractive on nearest neighbor sites. And I've done that in such a way that it will give me, if U is positive, it will give me a D-wave, uniform D-wave superconducting state in the absence of disorder. And this line here, so this is computed at some particular temperature. This is on a square lattice with Hopf elements 1 and with doping concentration 0.8. And this is the largest eigenvalue that we get in this case with U positive. And then we turn on various types of disorder. So here, blue is we put a disorder potential on every site, chosen randomly from a square distribution between -3 and 3. And in orange, what we've done is we've put strong scatterers on 10% of the sites, strong repulsive scatterers on 10% of the sites. That's 2 types of disorder. And in both cases, you see, even though this is a D-wave superconductor, that I haven't killed superconductivity. Okay, that's a surprise. In fact, even worse than that, I have eigenvalues in the disordered system that are bigger than those in the clean limit. So this violates Abrikosov and Gorkov. Should have been that I've killed everything by this point. And it even violates Anderson in that I've got an enhancement of superconductivity. Down here is the same calculation applied to if U negative, so X-wave superconductor. So here's the most negative eigenvalue, which if U is negative comes positive. So this is where I would get S-wave superconductivity for this particular model if U were negative. And you see that I have all sorts of states that are trailing off below here. So what? Yeah, so here we've done it a little bit differently. We've set a given temperature, and you can ask what value of U would there be at which T equal to that temperature. So that's what this determines. Okay, so in this case, U would have to be whatever it is to make this one. Okay? It's just numerically easier to ask it that way because we're looking at the linearized gap equation. Yeah? Yeah, so, okay, so this was a surprise, you know, this is what happens with students. My student came with this. I said, come on, don't come to me with such shit data. You haven't averaged over enough disorder realizations. So he went and he averaged over lots and lots of disorder realizations, and you still saw this structure. I said, you know, probably your systems are too small. Go to, you know, 5 times as large systems. So he did, and you still see all this. In fact, you started getting even more structure. So this structure is real. It's, you know, it's rich. I'll hint at where it comes from in a minute, but yeah. Anyway, he's no longer in physics. Yes.
Let's say we think of the system on some code. So what you have done is
On what?
So we think of that system.
What we've done? What?
So, I'm just like thinking how you would actually practically code this. So you have a system which does not have, let's say, translational
Yeah.
inside there.
Yeah.
And then you have a lattice, and then put, let's say, a random disorders into each site. So
Yeah.
some sort of
Yeah. Yeah. So it's a one particle disordered problem. So, you know, you're limited in how big of systems you can get, but it's not a many body problem. So it's just a one body problem. We have to get all the eigenvalues and eigenvectors. Then we compute the superconducting susceptibility at a given temperature by summing over all the states with the appropriate wave functions. And then we plug that into the gap equation, which is a linear equation, and then we diagonalize that. So, you know, it's conceptually simple. It's, you know, computationally trivial for people who, you know, think about classifying hard calculations are. You know, it was a lot of work. What? I don't remember. I think our biggest system sizes were 100 by 100, but I don't remember. Yeah, so that's what I kept sending my student back for. But yes, you know, as you go to lower temperature, so it depends, there's a trade-off, you know, so I wanted reasonably weak coupling, so I wanted to know, you know, when TC was 0.05 in units of the bandwidth. So that's still a TC that's very small compared to the Fermi energy. But the smaller the temperature you go, the larger the Thouless length is. So your system has to be big compared to the Thouless length, but it was in this case. So good. And, we also were at some point worried that we would have to worry, since this was 2 dimensions, that we would have to worry about localization, but localization doesn't, so even though we're at 100 by 100, we don't see localization physics at all, so. Okay, any other questions? Yeah.
How will you prevent the Cooper channel? So it seems any of effect like absolute error is not including the calculation. So do you expect the absolute error will be
No, sorry, we calculated so this problem, we're treating the interaction as a weak interaction, and so we're doing BCS mean field theory for that. So there are no interaction corrections because they're not supposed to be. The prescription of what we're doing is we treat the disorder exactly. Everything you can think of, we've treated exactly because we've done it numerically, but then, what we're, whoops, oh, I'm going in the wrong direction. What we're calculating is this quantity where these are properties of non-interacting electrons in the disorder. So if there were strong interaction effects, there would be strong interaction effects. So this is all within good metal physics, weak, Aronoff, if KFL is big and we're at some finite temperature like this, Aronoff, any of these corrections will be minuscule. But, we didn't conclude them because, this is what we're doing. We're solving a specific problem. We're asking, what happens if we do BCS mean field theory? So if I included strong Coulomb interaction, of course, off. Yeah, any other questions? Okay. Yeah. So let me do something a little bit analytic. So this eigenvalue problem that we have is we have some operator, and we're trying to find, it's a disordered operator, but it's local in space. And we're trying to find eigenvalues of it. And in particular, I want to find the largest eigenvalues of this. So let's really think about that. The largest eigenvalues are going to occur for rare occurrences. So what's the sort of thing we might have? Well, if this was a D-wave superconductor, we might look for a rare patch where there were no impurities. But if we were in an S-wave superconductor, we might look for a rare patch where the impurities happen to form a nice little cage, like that there was a big peak in the density of locally, but in some region. This is pretty contrived. This will be very rare. But if I find a region like this that has an enhanced density of states at the Fermi energy, then even for an S-wave superconductor, I'm going to find a big TC here. In fact, bigger TC than for the disorder-free system. Okay, if you can think of any configuration of my disorder, no matter how rare, that would enhance TC, if I look at a big enough system, I'm going to find it. So actually, this mean field level, I always expect disorder, regardless of whether it's D-wave or Q-wave or S-wave, should actually enhance TC. Okay, and so this problem is just very analogous to the tail problem in looking for rare events that give you tails below the edge of a band gap in a semiconductor. And so, you can carry over the beautiful work that's been done on that. And, you can say if T0 is sort of some average TC that I would have gotten in effective medium approximation. And I can ask, what's the density of regions that have a lambda that's bigger than 1, if I'm at a temperature above this sort of average TC, then that's going to fall off exponentially as you go up above the average value. And this expression is something that you should derive as a homework. I think derived first by Halpern and Lax, but then there are these beautiful instanton methods by Langer and Zittarts, and it can be derived from replicated field theory with replica symmetry breaking Carty. It's a problem. My gift to you is that you should go look at this. At any rate, the important thing here is this factor, which is the correlation length of the system, or the thermal length of the system at this temperature, divided by the correlation length of the disorder, which in the model I was looking at was 1 lattice constant, but I could generalize this to problems with correlated disorder. And so what you see is that if this quantity is big, that occurs in an exponential. These tails, okay, they exist, but they're going to be extremely. And so that means I'm going to work really hard on my mean field theory. Once every megaparsec, I'm going to find a region of space in which I get a mean field solution. And then the moment I include fluctuations about it, that's going to be coupled to nothing, so it's going to commit suicide. So I will run a much better calculation on mean field theory and gotten a result that's sort of idiotic. Yeah.
Claim that I was doing theoretic continuum, and my disorder covariance was but that's the setting in which, for example, all the work by all these greats for the Lifton-Stale problem.
Yeah, so this is a little bit different in that sense. But yeah. I mean, they do some cutting off there. It's a, asked me that before. I've been thinking about it. I will go into it, but I don't want to go into that right now. So, so what Akshat's asking is, suppose I take the limit that the disorder correlation length goes to 0, then that cuts things off completely. Okay, let me go on. This was the linearized gap equation. Let me do something that's more easy to translate into the physics of cuprates. So here we're going to take A, which I'm afraid we chose the band structure. So we had a first neighbor hopping and a second neighbor hopping of the right magnitude to reproduce the cuprate phase band structure. I wish we hadn't, because it sort of invites you to take the results more seriously than they should be. But okay, that's what we did. And then we turned on random site impurity disorder. So W was chosen randomly in a square distribution. And for the results I'll show you, it's chosen to be range between minus, where 1 is the nearest neighbor hopping here. And mu, sorry, that's not what it was chosen. Wi was chosen to be either 0 or 1 with a concentration X. So we were thinking of varying impurity concentration. Impurity site Wi was 1, non-impurity site Wi was 0. The chemical potential was chosen so that when there weren't any impurities, the concentration of holes was 15%. But then when I introduce these impurities, I'm also changing the average chemical potential. So the density of electrons are changing in such a way that the system is becoming more and more overdoped. And so again, I wish we hadn't done this. This invites you to take the results too seriously. So we're going to plot results as a function of hole concentration, starting from optimal doping and going on. Okay, but all right, this is what our model was. And then for the interaction, we took either an attractive on-site U when I wanted to study what the effects were for S-wave superconductivity, or a nearest neighbor J. Both of these are going to be treated in mean field as going to be decoupled in BCS mean field theory. So don't take too seriously what we've written down. These are just, but I wanted you to know what it is we're studying. Okay. And so here's a picture of what comes, and we're going to look now at zero temperature. So we're going to study the full nonlinear gap equation and find the solutions of it. And so here's at some moderately low impurity concentration. Somehow this N impurity is drifted down. I don't know why, but, and here in the D wave case, red means we have a pair field on that bond that's positive, and blue means we have a pair field on that bond that's negative. So you can see the D wave structure here. The depth of the color tells you the strength of the pair field on those bonds. And you can see that the D wave solution is notably inhomogeneous here. Whereas the S wave solution, well, first place it's S wave, it's all positive. And even though we're at this same impurity concentration, it's much more homogeneous. And now I'm going to crank up the impurity concentration. And so here the S wave is still, not very changed. So Anderson's theorem is at work. And here on the D wave case, the systems become enormously inhomogeneous. So still in these regions, it looks more or less like it did at lower concentrations. So we still have regions with very strong superconducting pair field correlations, but there are regions where the pair field correlations are very weak. So this looks like sort of superconducting regions embedded in a metal framework. No. This isn't disorder average. This is take some disorder configuration and calculate. I mean, disorder averages would have to be homogeneous because the disorder is chosen to be homogeneous. So these are all for a particular configuration. These are quite a bit smaller systems because solving the nonlinear, the full gap equation is a much more complicated endeavor.
Steve, the S wave still looks somewhat, inhomogeneous.
Yeah, I mean, there are a few places where maybe the gap scale is a factor of 2 smaller than average, but it's not a big effect. It's nothing like in the D wave case.
Can it be quantified?
Yeah, so here's some sort of average properties. So here's the average over the sample of the local pair field strength. And as you see for the S wave, the average doesn't change much. So indeed, there are some regions that are a little bit stronger than they were and some regions that are a little less, but the average doesn't change. Somewhere or other, we plotted the mean squared deviation, but I don't have a plot of it, but it's relatively small, yeah?
Binary, just like strong or weak.
Yeah. Well, I think that there's sort of, must be clean regions where there are no impurities. So the fact that the strongest bonds are of some strength, that's more or less what it was in the clean limit. But there are sort of some intermediate regimes. It's, you know, these regions are not sharply defined. This is a metal, and so the superconductivity leaks out in all sides of this. So, okay, yeah. Yeah, so that's why I think I don't think you should be thinking about percolation because, you know, the fuzziness in the edges of the region is comparable to the size of the distances between regions. Also, as we discussed in my previous talk, the superconducting correlations, at least at low enough temperatures, fall off like a power law in the metallic regions. So if we looked closely, we would probably see that these are not becoming suddenly zero, but there's power law dependence here. So, so thinking about classical percolation is probably not a good idea, but yeah. No, but you know, it's going to be something more complicated. But here, if the pairing field is weak, then it should be almost a metal. Then it should be almost a 1 over r to the d. The thing that's going to cut off the r to the d is the induced proximity effect there. So okay, so I don't know. Anyway, it really is a complex. I mean, this is a complicated problem of wave interference, and you know, the gross characterization of in terms of much more superconducting and much more metallic regions is clear. But if you try to push that too hard, you're going to get into trouble. Yeah.
We think of them as a metal because there's still disorder in it and it's 2D.
Yes, but the disorder is weak enough that the localization lengths are, you know, from here to Alpha Centauri. So, I mean, yes, in principle, metal is localized, but on the length scale we're looking at, that's you know, that's like saying that there are tails above TC in aluminum. It's probably true, but not of any relevance.
For a T plus ID superconductor, which is gap filled.
That's what?
The T plus ID superconductor.
Yeah. I expect the same thing. I don't think this has anything to do with nodal particles. I mean, I haven't done, but I don't think that should make any difference. In fact, I'll show you, this is actually a time reversal symmetry breaking superconductor. You didn't know that, but I'll show you that in a minute. Yes? Well, by definition, since my ensemble is translationally invariant, any quantity that I compute that's in configuration averaged is going to be translationally invariant. Yeah, that's before averaging. And then if I had another configuration, it's going to have a superconducting puddle over here. So the picture that I showed on the next page, this picture, which is the spatial, is the average over space, but the average over space should give me the same thing as the average over configurations. So if I did the configuration average value of the pair field on some x directed bond, I should get this. Right. Okay, I haven't checked it, but I see no reason why it shouldn't be self-averaging. Yeah.
So what is the correlation between that disorder profile and this pair?
No, I mean, so, you know, we have 25% of the sites have impurities on them. So this is some collective effect. You know, I suppose we could try to do correlations. You know, what I suspect is that there's sort of less impurities in this region and more impurities in that region, but I haven't honestly checked it. But it's not one-to-one. These are relatively weak impurities, so it's not that near this impurity you see a killing of the superconductivity. Yeah. Yeah.
I'm just questioning whether, if you're at zero temperature and weak disorder, there's no really linearized.
This isn't the linearized equation. So here we're studying. Yeah, no, but for that, the data that I'm showing you is the solution of this equation. What?
Yeah, that's the full one. I'm just questioning the existence of this equation. There's no, at zero temperature, there's no equation.
No, that's right. I mean, there is an equation like this, but it's not a sensible equation because chi is infinite. That's right. So this is all at finite temperature. Yeah, all of this is done at finite temperature. So as I said, the range of this thing is determined by this thermal length. So this thing becomes extremely non-local as I go to low temperature. Yeah. Now I understand what you were asking. I agree, and I agree with you. You can't do the linearized equation at zero temperature. But this stuff is all the nonlinear equation, and that's perfectly fine. Okay, let's just look at this for a minute. Here we see that, you know, the S wave does exactly what Anderson told us it would do. The D wave starts out doing more or less what Abrikosov and Gorkov told us it would do. But then as TC gets substantially suppressed, there are these tails having to do with rare regions where there's less disorder. This is the superfluid stiffness, again, computed in mean field theory. I'm not including any quantum or thermal phase fluctuations. We're just asking how much energy does it cost to twist the phase in mean field theory. And so here you do see that it is having some effect on the superfluid density in the S wave case, as it's supposed to. I think I wrote an expression on the board. It should be going down like in proportion to the mean free path. But for the D wave, it's dropping much more precipitously, which isn't so surprising because here, although we have superconducting grains, we've got metal between them. So we have weak links. And so the phase stiffness you would expect to be dropping in a much more precipitous way than the average order parameter. And you can see that better by plotting it on a log linear plot. So here's the suppression of the root mean squared order parameter, and it is being suppressed with disorder, but the superfluid stiffness is being suppressed much, much more rapidly. So we're going to rapidly get into a regime where indeed T theta is small compared to at least the mean field T delta. Yeah. This is the D wave case here. We haven't looked at the spectral function actually. I mean, and we haven't looked at SDM, but we have looked at specific heat. But I can't tell you about the D wave nodal quasiparticles. What you see here is the specific heat looks more or less like the normal metal. So it's dominated by these regions. I probably have a figure, I'll show it later, but you know, so I was telling you, I don't want you to think in terms of clearly defined superconducting regions and clearly metal regions. Okay, so now I'm about clearly defined metal regions, but from the point of view of the specific heat, you see a T-linear specific heat with out here a magnitude that's almost the same as in the normal state. So there really are regions that, at least to some good approximation, behave like a normal metal, and those dominate the low energy spectrum of the system. They probably should, yeah. No, this shouldn't be described by dirty D wave at all. I mean, this really should be described as an inhomogeneous mess. What? We didn't really calculate it, but it should be, it should be like, I don't know, 10 lattice constants, 20 lattice constants, something like that. Yeah. The mean free path is long compared to KFL is big. Then that's also why we don't see any effects of localization. Just an interesting note, you can also calculate the ground state current density. And, well, you can't really see it, but there are arrows. All right, you can't see it. It turns out that within this mean field solution, in the D-wave case, the solution isn't real. That doesn't mean it's wrong. It means it's not a real number. And so there are equilibrium currents having to do with the interference between paths that connect you from a positive lobe of a strong superconducting region to the negative lobe. And so there are all sorts of complicated spontaneous patterns of current density. So somewhere here as a function of doping, at least at mean field level, there actually is a phase transition within the superconducting state to a time reversal symmetry broken glassy state of some sort. Whether there's any physics in that, I don't know, but that is an absolute feature of the mean field solution. Okay, let's skip that.
In opposite senses, or is there a net average?
So you remember I have one configuration. And so, yeah, so locally, I mean, of course, if we took there must be a second solution, the currents reversed. But, there's some plaquettes where there's currents going around this way, and some plaquettes, it's a glass. It's not a, so it's little current loops, directions, and some complicated, and they're very weak.
Wondering if this would be, when observed in a material, whether you would see a net time reversal breaking. So
be like a spin glass, like an Ising spin glass, exactly. So the answer is yes, but you have to be a little subtle about it. All right, so good. When I'm supposed to end in 6 minutes, is that right? Okay, let me show one more picture, just because it's so beautiful. So this is some old data from Ali Yazdani's group from 2007. This is an overdoped sample of Bisco with a 61 Kelvin T. It's overdoped, so it's less vexing whether we're seeing a gap or a pseudo gap, but okay, that hasn't been addressed. What's being plotted here is locally in space, the magnitude of the gap. That is to say, you see peaks in the density of states, and you report 1/2 the distance between those two peaks. And you can see that here we're at what temperature? 50 Kelvin. So we're 10 degrees below TC. And you see there is some variation in the gaps. So this looks a little bit like the pictures that I've been showing you, where there are some places where the gap is maybe, I don't know, 35 millivolts, maybe almost 40 millivolts, and other regions where it's maybe half that. Maybe one or two regions where it's even a little less than half that. But, there's sort of factors of two in the gaps in small regions. What?
There's also, in your picture, you could also tell the variation of orientation of the D wave gap.
No data about that here. This is just measuring a scalar quantity. Yeah. So we actually, in all of our pictures, we have an overall sense of the D wave. There are some local places where it's reversed, but overall it's dominantly the x-directed bonds are positive, the y-directed. What? I mean, D wave superconductivity doesn't really break C4 symmetry, but yes. Yes. Okay, but the thing that's unique about, so data like this exists for lots of people and lots of materials, but what's nice here is that he gives us data as a function of temperature, and we raise the temperature up through Tc. So here's what happens. So of course, the gaps get smaller, but they get smaller in very inhomogeneous ways. Now we're at Tc, and there are regions where the gap is 0 and regions where the gap is as big as it was below Tc. And here we are now, I don't know, 16 degrees above Tc. Most of the system is gone, but there are still regions that have, more or less as big gap as they did at low temperatures. Okay, so this is sort of the solution of the linearized gap equation. And so these are these little patches I was talking about where, maybe here there's no impurities, or maybe even better, there's a cage that makes some big density of states. And in the rest of the state system, it's more normal. And as Leo said, the problem is more local at high temperatures. So it makes much more sense to look locally and ask, what is Tc? Whereas as I go down in temperature, here's the big question, is if I can do this. No, I can't. Okay, well, let me just show it to you one more time. So the point is, well, here's at low temperature. So this is presumably the same disorder configuration, but the problem becomes much more homogeneous. I mean, it's still granular. This isn't super overdoped, it's Tc reduced by 30 or 40%, but you really see this picture. I mean, this is a super slow experiment. So, each one of these pictures takes many days just to get the picture. So we're not seeing any reasonable dynamics in this picture.
In particular, one should expect that this is all equilibrium. That's very configuration that.
I mean, look, you're a glassy guy, and, in glasses, there can be realization rates that are as long as you like. So I'm not going to, fall into that trap. But, for most purposes, this is, really static, long time equilibrium behavior. Yeah. Yeah, I'm a equilibrium sort of guy, big and slow.
Configuration changes as you change temperature.
Yeah, I understand. So I don't think there's any reason to think that atoms move around at these temperatures. So I think the atomic configurations are frozen. Now, what? I know. I mean, what would be an interesting question, which I've asked, you've gotten the impression that my students avoid me because I ask them too many questions. All my friends avoid me for the same reason. So, what I wanted Ali to do with this is to then cool down and repeat the experiment and compare the results. And as I said, we're friends again.
Why did it take? What are they integrating over that it takes so long to get this? They said days.
So, they're rastering their STM tip, at each point in space, they have to take a spectrum. Then, move to the next point in space and take a spectrum. So there's, you can see there's, a gazillion points here, and each point is a full spectrum. And, the reason you don't see much data like this is that it's real. Then you change the temperature, and as you change the temperature, your substrate expands or contracts. Then you have to find the same spot on the sample to be able to say that you're looking at the same. This is really a heroic experiment. Yeah.
Anything happens specifically at 61 Kelvin in the image, like observer?
It's hard to see anything particular. Let me see if I can. Let's get out of this mode. See, how do I make this thing big? Did I stop it? Good. All right, so that's okay, that's almost at TC, that's 59 Kelvin. And so, I don't know, you have some empty regions, it's not, that's 61, that's TC. I don't know, I don't see any particular at TC, but all right, good. Let me take 2 more minutes to say, okay, so first place, so my conjecture, so this is all, absolutely clear within BCS theory. I can get a state out of BCS theory and D wave with a short coherence length in which the disorder is responsible for both suppressing TC and for even more suppressing the superfluid stiffness. Noga will present a poster where we start from the proposal that if we kill superconductivity with a magnetic field and look at what the metallic state is, which you have scattering off small superconducting islands, that can give you an account of this strange metal. So, although I didn't get to it, I think that with a little bit of imagination, you can imagine how this physics can allow us to reconcile this with being the underlying ideal phase diagram, and this, which looks nothing like it, being the measured phase diagram. Now I think my boss tells me I should stop.
What's the argument against that theorem?